9, section 9.2, hypothesis testing for the difference of two proportions. So last time we looked at confidence intervals. Today we're going to look at hypothesis tests. All right, so when we are looking at hypothesis tests, we still have the same three conditions that we need to be using, making sure that we have random, independent, and approximately normal, but now we have to make sure that we're still checking it for both populations. And so that's where it slows us down just a little bit as far as making sure that they're met for every population that we have. So in this case, two proportions. The statistic that we're going to use as our best guess is the difference from our two samples. And that should be a really good estimate for the difference of the true proportions. The standard deviation or error that we're using is the same one that we used for our confidence interval. And so what we're going to look at today is the significance test. And so again, this is a claim that's been made. And for most hypotheses that we're going to do, we're going to claim that the null hypothesis assumes there is no difference. And so while we can write it this way, where P1 minus P2 equals 0, meaning that there is no difference between them, they are the same number, subtracting two numbers that are the same should result in 0. I will typically write it this way, where it says the null hypothesis is that they're equal. That way my alternatives can say, oh, I think P1 is actually going to be smaller than P2, bigger than, or not equal to. And so that's kind of where I like to put this in the middle because I can see it easier for the alternative here. And so when we're doing a significance test for a proportion, we're still going to use our z-test statistic. So we're going to see how far is our sample statistic away from what's been claimed, 0, out of the standard deviations. And so that's where we want to make sure that we are looking at how far away. If it's 3 standard deviations away, that's going to give us a really small p-value. 5 standards away, it's like almost 0. Half a standard deviation away, at that point we're thinking it's just sampling variation. So we need to report the test statistic, our z-value, and the p-value that goes with it, the proportion or the probability of our sample happening. All right, so here's our first example. It says, in a study of 3,000 randomly selected teenagers in 1988 to 1994, 15% showed some hearing loss. In a similar study of 1,800 teenagers in 2005 to 2006, 19.5 showed some hearing loss. Okay, so does this data provide convincing evidence, there's that phrase that's going to tell us to run a test, of a difference of proportions? Carry out an appropriate significance test at the 5% level. All right, so the first thing we're going to do is define our two proportions. The first one I'm going to define as our 2005 group here. So I'm going to say this is the proportion of teens with hearing loss in 2005, 2006. And we want to compare that to what it was before, the proportion of teens with hearing loss um, 1988 to 1994. All right, so here's what we're testing. We want to make sure that we're defining our variables so that we can keep straight. I have the first one being the 2005. I have the second one being the 1988. You can switch these as long as you're defining it and using it consistently. That's fine. So if you saw the first one just going in order, that's totally fine too. The claim that's been made is that these two proportions should be the same. They're teenagers. The proportion of teens with hearing loss here should be the same proportion in the second one. However, it says, is there a difference in those proportions? Okay, so we want to know, are these two things different from each other? Because what's this telling us is that maybe there has been something that's changed from 2005 compared to where it was in 1988. So we're going to compare this at the alpha of 0.05 level here. And the way we're going to test that is we're going to do a 2 sample, one from each of those years, z-test, and check conditions. All right, so for checking our conditions, we need to make sure that both are random. Okay, so we're going to double check that these are randomly selected here in a similar study. So we're going to say that is random. 10%. Okay, so for the first group, we had 1,800. I'm going to multiply that by 10 and make sure that that's smaller than the first population. Should be plenty more than 18,000 teenagers there. And the second group, I'm going to have 3,000 multiplied by 2. And again, for the second group, there are more than 30,000 teenagers in 1988. So we've met the independence requirement. The third thing we need is that we need to have large enough to become approximately normal so that we can use the z value here. So large counts here. All right, so for the first population, we're going to look at my 2005. I have 1,800 times 19.5%. So how many successes is that? So I'll do 1,800 times 0.195, and I get 351 successes. And in this case, a success is hearing loss, so I'm not sure if that's a success there. But this is bigger than 10 or equal to, so that passes. So how many fails do we have? We'll take 1,800 minus the 351 we expected, and we get 1,449. Okay, also bigger than or equal to 10. So once I've checked it for the first, let's check it for the second. I have 3,000 with 15% expected. 0.15. And so I have 450. I'm going to go ahead and grab that other number here. Minus 450. And so we get 2,550, so 450. Both of those numbers are quite large there. So they've taken a large enough sample to make sure that this will become approximately normal. We've met that z condition, that normal approximation here. So now we're ready to do the test. I need to report my z critical or my z score here. It says tell me how far away am I from what I expected. And then I need the p-value. So just like we did on our test before, I'm going to use this on my calculator. I'm going to do a 2 sample prop test here. So 2 sample, let's pull up our menu. And I'm looking for a 2 prop z test. Again, here's a 2 sample z test. While that is the name of the test we're doing, if I open this up, it's going to ask for all kinds of standard deviations and lists of data. Oh, we don't have that. So if you pull up the wrong menu, that's okay. Don't force something into that just because you're convinced that it's there. Let's try something else. Go back to the menu. 2 prop z test here. And the first one we have, I'm going to go ahead and pull up 351 out of the 1,800. Oh, let's make sure we have the right number there. And then the second one is 450 out of 3,000. All right, so we're observing a difference of 4%. So in my head, 4.5%, something significant there. And we're claiming that P1, and again, this is another reason I like to put the sign in the middle and not bring in the 0, is because it allows me to say, okay, we think they're equal in the claim. Our alternative is that maybe they're not equal. I still like to draw it out here, and it'll give me my z value and my p value. All right, so there is not a lot covered in here. In fact, they're giving us a z of 4.048. So here's what's claimed if they are equal, and our sample is 1, 2, 3, 4. I mean, that's why we're not seeing anything. It is 4 standard deviations away from what we expected. So this is about 4 points. what was it, 0.04, so 0.05 there, with a p-value of 0.00001, I think is what it's saying there, 1 e to the negative 4. I think I have one too many zeros. Move it over one more. Because that would be 1, 2, 3, 4. There we go. All right, this is a small probability. And think about how far it is away from what we expected, which is why in our conclusion, okay, we would say because p-value, which is 0.0001, is less than alpha of 0.05, we reject the claim. Okay, that 4%, 4.5% difference we're seeing is significant. We found evidence that there is a difference in the two proportions. Of teens with hearing loss. All right, so that 4%, I had a hunch. I was like, wow, that's really kind of far from what we expected. Statistically, that agrees with me there. So, if we were to have a follow-up part that says, if there is convincing evidence, okay, we had that. Can we blame Apple's iPod that came out between the two studies for the cause of the increase in the hearing? Okay, so this is that idea that goes back to almost unit 1. This is a causation idea. Can we say that in between those two studies, there is a significant loss of hearing? Can we blame Apple's iPod? This idea of cause has to do with the design of the study. This is an observational study. They didn't know that something was going to change. They just kind of investigated it. We cannot say that this was a causation. So causation has to be in an experiment. And again, this was not an experiment. It was an observational study. So can we blame them? No. Can't blame Apple. That would be a lot of money, though, if they could. Not an experiment. Or you could say it was an observational study, something along the lines that say why we can't use the word cause. It wasn't an experiment, it was an observational study, something like that. All right, let's look at another example. In an example, it says, in an effort to reduce healthcare costs, General Motors sponsored a study to help employees stop smoking. In the study, half of the subjects were randomly assigned to receive up to $750 for quitting smoking for a year, while the other half were simply encouraged to use traditional methods to stop smoking. None of the 878 volunteers knew that there was a financial incentive when they signed up. At the end of the year, 15% of those in the financial rewards group had quit smoking, while only 5% in the traditional group had quit smoking. Do the results of the study give convincing evidence that a financial incentive helps people quit smoking compared to traditional methods? All right. So again, this is one of those things where we want to make sure that they're looking at the experimental design here. None of the volunteers knew that there was a financial incentive. So they all are in the same boat. They would like to quit smoking. General Motors is running this study because it costs a lot of money to help people when they're smoking. There's a lot of health benefits to quitting, and there's a lot of cost to keep smoking. So as someone who helps pay for insurance and health insurance, General Motors is enticed to make sure that they have healthy employees. That's going to be something that they want there. All right, so we need to first define our two variables, okay? We are going to look at the first and second one here. And so as we look at the first one, I'm going to say this is the group that had incentive. And so this is the proportion of smokers who quit smoking with the incentive, so money incentive. And the second group we have, and again, P, always start with the proportion. Mu, always start with the mean. So I'm going to still repeat that. This is the proportion of smokers who quit with traditional methods. All right, so originally the hypothesis here should be that these are all people that want to quit. These groups should be the same. Whether you're getting paid to do it or traditional methods, these proportion, everybody wants to quit. However, it says, do the results of the study give convincing evidence that a financial incentive helps people quit smoking? So they're hypothesizing that paying people, our first group, will be bigger than the second group. And they haven't indicated, I almost saw that 5%. I was like, they haven't indicated alpha, but we'll keep it at 0.05 here. All right, so our plan to test this hypothesis is to do a 2-sample, we have 2 different populations, z-test, and make sure that the conditions have been met for both populations. So make sure that we have randomly selected. Okay, well, this is randomly assigning them. So even though we have volunteers, we can't make people smoke. That's not something that we could just pick 878 people off the streets and say, okay, you're part of a smoking study. And it's like, whoa, 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 I do not smoke. So I can't be part of that. They were volunteers, all similar in the fact that they were wanting to quit smoking. And so they randomly assigned the 2 treatments. And so in experimental design, that's our random condition. 10%, again, if we had our 2 groups here, so 878 divided by 2, 878 divided by 2, so we have 439 in both groups. I mean, at this point, each person should be independent of the other, so one person stopping doesn't affect the next, but we can check that too, and we have 439. Okay, if they had access to that many smokers, it would be smaller than the population of all smokers in the first. And again, this is kind of overkill. We don't necessarily have 2 separate populations because this would be a pooled idea that all of the 878 volunteers, but if we had access to this, there are definitely more than 8,780 smokers. So both of those groups, we could randomly assign them to be part of the incentive group, and we could randomly assign them to be part of the traditional methods group. This will be met. Again, we're checking independence. One person smoking shouldn't be influencing the next one in a random assignment there. Okay, large counts here. Okay, I'm going to check for the first one. So that's our money incentive here. So 15% of our 439. So I'll take 439 and multiply by that 15%. And so we got 66 here. So we had 66 people that did quit smoking. And then how many did not at the end of the year? We'll take our 439 minus that 66. And we have 373 that were not able to quit smoking. Don't start. That's the way you don't have to quit. Both of these are large enough to become approximately normal for our first group. So then we'll check the second group. We had 439 and 5% of those. So 439 times 5%, 22 in the non-incentive group quit smoking. And if we subtract that from 439, we had 417 that did not quit. So total in this study, we only had 88 people that were actually able to quit smoking. And that, I mean, again, it's an addictive substance. So in this group, they did have some success. And right now we're seeing a difference. 66 compared to 22, 15% for the first group and only 5% for the second group. Is that 10% difference significant? Well, let's run a test to figure it out now that we've met all the conditions. Let's find the z value and the p value associated with it. Let's see how far apart those two values are. All right, so on my calculator, I'm going to go to Stat, Tests. I'm going to do a 2-prop z-test, not tempted by that 2-sample z-test. And then we would have 66 in the first group out of the 439. And on the second group, we had 22 out of the second group of 439. And we think that P1 is going to be bigger than P2. And again, I prefer calculate or draw. Draw is my favorite here. So it's drawing in, nothing over here, and nothing over here. Whew! All right, they're saying that our 10% difference that we're observing is 1, 2, 3, 4, almost 5 standard deviations from what's claimed where they would be equal. My calculator is even saying that's a probability of 0. I want to run this again just to see what it says on the calculate side. I'm not sure if it'll give us a 0. It still might try to give us a decimal. It does. It still gives us that 4.94 z value, but look at this, 3.81763336 e negative 7. That's 0.00000004. That is essentially, for our purposes, 0. So for this, we're going to say we had a p-value that is 4.9, almost 5, which gives us a probability of 0. So our conclusion, because p-value is equal to 0, which is less than any alpha, but we chose at the beginning 0.05, we reject the claim. We found convincing evidence that and it's almost like repeating that sentence, that the financial incentive helps people quit smoking. All right, so here's our 2 things with proportions. We did confidence intervals and we did hypothesis tests. Spend some time making sure that we have the hypotheses set up correctly and that we've checked conditions not just for one, but for both groups. And so the last part here is those calculator things. And I want us to make sure that we're drawing our eyes and remembering that these are going to be 2-prop, 2-proportion z-test, 2-proportion z-interval. And so these are our calculator reminders in case you need that. I prefer draw when it tells me that, just because I can see what's been claimed here in the middle. Here's the claim. So if there's a lot shaded in, fail to reject. If there's like nothing visually shared or shaded in, we're going to fail to reject. I said that the wrong way, didn't I? I like draw because it tells me how far away it is from the claim. Close to the claim, fail to reject. Far away from the claim, reject. Oh boy. All right, let me know if you have any questions.